I own from this position to this position. So they don't need to contend for any sort of block, and they can just keep writing in the 10 megabyte block until they run out of space, and they go back to block allocator, which will create a new file and keep going. What's the point of this? The whole point of the system is to reduce the block contention. Instead of taking a log every single time you write something, why don't you take a log after writing 10,000 entries? This single thing, it usually reduces contention and increases write throughput. Yeah, so I talk about block allocator, what the hell it is. We have here 3 log files. Let's say topic X owned this block, then on some other topics were writing in this block allocator, allocated this block to topic X, some other topics came and got this. So how does it look like? So let's say the writer was able to write 5 entries and the block got full. So 0 to 5 entries are here, it was able to write 5 more entries here, and the rest of the entries here. One downside of such a system is that because you're scattering your writes, you need to keep track of them, because I'm assuming if you're writing something, you're eventually going to read them. So yeah, this thing results in a scattered metadata. You need to keep track of a lot of metadata, like this topic, we have entries 0 to 5 here, in this file, entries 6 to 11 here. This is the scenario. So how do you keep track of all the metadata? So in order to read it, you need the metadata. We store them in the disk, in metadata files. So what do readers see? In such a scenario, the entries are spread around in 3 files. Readers need to see continuous stream. Readers don't bother with A050. All it cares was just give me all the entries from 0 to 17. So how does this work? Readers are usually entries and some jargon here. Once a topics writer has moved to this block, this one is considered sealed. It's just some jargon, might come helpful later. Readers are usually entities. Once something has been sealed, a reader can just move through it like a pointer. All the reader needs to know is which block am I reading and where in that block I am. And because of this metadata, it just sees the log as a infinite log. It doesn't know anything is scattered around. And readers need to have consistency mode. So Kafka offers at least once delivery guarantee. Once you read something, it doesn't matter if the system crashes right after that. It boots up and you don't get any duplicate entries, so you don't have to deal with deduplication on the application level. Or if you wish to have better read throughput, and you're fine with deduplication on the application level, you could choose this consistency mode. In this, basically we just flush the read index every once in a while. So if it crashes, you might see some duplicate entries in Kafka. One of the very major problems that comes with such an architecture is in Kafka, this deletion part is pretty similar. It just keeps track of, it doesn't need to bother with these blocks, it just has a file and it has one pointer per file. When it sees that the pointer has gone past that limit, it can just delete that file. We don't have such privileges. Because we have a bunch of writers scattered through the file and a bunch of readers. We don't know if a file is safe to delete. Because the writers are not aware of each other. The file could be being written to at any point, or being read, or it might not have been fully allocated. For example, these blocks, they could be free and the file could be deleted. So we need to keep track of all such scenarios. And if we were to have a central coordinator who would do all such things, it would kind of break the whole point of our system, because the whole point is there are no contentions. There's no central coordinator, no one needs to know about each other. Topic X doesn't reach from a topic Y. So how do we tackle this part? Well, we go a little bit deeper into systems programming. We have 4 variables, system variables. These are atomic counters. Essentially, we track 4 atomic counters per file. How many blocks have been allocated for this file? How many blocks have been checkpointed? When I mean checkpointed, how many blocks have been read by the readers? And how many total blocks are in the file? And is the whole file fully allocated? So how does this all works? Every single time block is logged, it means it's been actively written to. We just increase the number of this. Once the writer goes past that, we automatically decrease that. Once a block is checkpointed, we just increase the counter, and just like that. So with this way, we don't need to keep a central authority. Every single time any one of these 4 counters update, we just check, are all the other conditions met? If they are met, we can be sure that our file is safe to delete, no one is reading to it, no one is writing to it, and it's fully allocated. And yeah, that's the problem of asynchronous deletions. The problem in these Kafka-like systems is that the read and write parts, they are called the hot parts, they're holy, because we need to keep track of, make sure the latency is low, that, the throughput stays put. But the problem is, let's say, if you're deleting everything in a hot part, it means you're writing something, you realize that, oh wait, I can delete this file. If you go on and delete that file, and at the exact same time, your latency will just go ahead, because you're not the only person writing to it, there are a bunch of other people. And deletions can be super expensive. So in our architecture, we defer it. We have an asynchronous background task system. We just enqueue the deletion of the file, and eventually a single-threaded worker just picks it up and deletes it. And since it's single-threaded, we don't need any consensus or anything. And yeah, we have one more thing that Kafka doesn't have. Walrus has transactions. You could have batch appendation for topics. For example, you could choose to ingest 10 entries, and the system would just make sure that either all of those 10 entries get ingested or none of them get ingested. Essentially, you could, let's say, you wrote like 10 entries, you wrote 5 entries, and the disk got full for whatever reason. Then the system would just detect it and roll back. This is some database lines. So how does this work? Well, let's say you send a request for batch append for this topic. I just want to ingest this particular batch. We'll just validate everything. Then we have a planner. This is very similar to a database query planner for those who work with databases. Since our system is scattered, let's say we want to put 10 entries, and they are like pretty big. They're like 1 gigabytes. They sum to 10 gigabytes. In Kafka, it's pretty easy. They just append 10 entries. It's just a blob append. In our system, we don't have such luxuries. In our case, some entries could be here. The file could get full. We might need to roll it over to the next one. That's why we need such things. So we need to plan how many blocks should we append or should we give to this. And we also need to keep track of the original state, because in case something goes wrong, we need to roll back. We need to calculate the space, how much space. What the system does is it just pre-allocates a bunch of blocks for a transaction, writes that transaction, and once it's done, it uses IO, which is a most modern way of doing IO on Linux, and then it verifies. Did all writes succeed, or some write cause failed? It's nothing failed, all good. We just validate everything and release logs and send a success. In the case of failures, this is where things get interesting. Remember the time I told you that we keep track of metadata? Metadata in the sense that we keep track that I'm allocating this block, this block, this block for this topic. Well, that's useful. When we realize that some writes fail, we will need to roll it all back. So what we'll do is, we'll just, we'll just kind of, because since we data can be heavy, we don't want to, actually mutate the whole data, because let's say you're writing 10 gigabytes, you wrote 9.99 gigabytes and then it failed, and you have to roll that 9.99 gigabytes back to the original state. That would be too expensive. What we do is, we just mutate the metadata such that next time a write comes, it will just overwrite them. You don't need to manually clean it up. What's the point of this batch writes? The magic of this batch writes is that you can do more with less. For example, when you are writing one entry at a time, you need multiple threads just to reach 500k entries per second. But with this batch write, a single thread can gain 500k entries per second, and it just scales up. And with 7 threads just 7 threads, the I/O got saturated on my Linux box. We were getting around like 1.2 billion entries per second. And the good thing about this batch writes is you can kind of amortize the cost. With a single write, you would be doing a bunch of things. It would take around 2 to 10 milliseconds. But let's say you could do 10,000 writes in a single call. If you amortize it, it would be like 100 to 500 microseconds per entry. If you care about throughput, that's massive in a way. Walrus has a bunch of other things. It provides isolation. Let's say you could have multiple logs. Let's say you have an event log, a key value store, or essentially a time series database, or a message queue. You could use it as an in-process system as well. So in-process system, your main application could have totally separate log streams. And a single Walrus instance could handle that. And just so how are these files laid out on the file system? This is how it looks like. These files are Walrus files. This DB thing is a read cursor. We just store the last requisition. And these are the files. These are data files which get deleted eventually once you read them. Walrus can also be used as a library. It's written in Rust, so you could just create something. Just when you're creating the Walrus instance, you could choose the read consistency. You could also choose the write consistency. Now this one is an important part because let's say not everything is equal. Not every log is equal. Let's say you're doing financial transactions. You don't want to lose something in that case. So you can choose fsync. Fsync is essentially something that, okay, who knows what fsync is? Yeah, so you can choose fsync on each write because it's important. You don't want to lose data. Or if it's nothing, it's just something, if these are just logs, I'll be fine if I lose a few of them. And I just want to use this thing as a fire hose. You can just choose to fsync every 200 seconds. So in case something crashes, you might lose a log or two. Here comes the graph again. This. Oh yeah, this one is important. This graph doesn't use fsync. It's kind of the Wild West. Everyone is just writing. So in case of power loss, the system could lose data. So if you were to use fsync on sync each, the whole point of performance kind of just collapses. Everyone is equal when they're just syncing on each write call. It's found interesting. Yeah, and Walrus has a very simple client protocol, unlike Kafka, which Kafka. This is very similar to how Redis handles things. Let's say you want to register a topic. You can register it. You want to append something to a topic. You can just put, in order to consume something, you can consume it. One interesting thing about Walrus is that, unlike Kafka, in which you have to keep track of offsets on the client level, essentially your clients need to be stateful. each client needs to know, hey, this is where I read from last time. Walrus doesn't have that. Walrus handles this part on red cursor part on the server level. So a client would just have to, just get me the next entry which I haven't read yet. This is essentially helpful when you have one server and multiple clients. One client can read one thing, the other client can read the next thing without any coordination. The server just handles it. Bunch of things, segmentation. Oh yeah. Okay, who here knows about TLA plus? Yeah, so these are essentially formal verification methods. Essentially with this, you can kind of verify the correctness of your algorithm. Correctness in the sense that you can verify that nothing wrong happens in massively parallel scenarios. Essentially, you can sort of specify some invariants. For example, before writing a single line of code, you could be like, okay, yeah, my system shouldn't read or shouldn't lose data, so things should be consistent. I want to make sure that no one steps on each other's toes, especially in systems like ours. We want to ensure that we are not, reading the same entry twice, and we want to read things sequentially. So TLA plus is a form of formal verification. Essentially, you can just verify your system's model very quickly. This is more of an academic part, but I just did it for fun. So yeah, some of the things about Walrus cluster. Now comes the distributed systems part. Walrus has segment-based sharding. Yeah. So consider this scenario. You have a cluster with 3 nodes. When a Walrus cluster boots and you register a topic, for example, logs, the metadata would get replicated across the whole cluster via enough consensus. After that, the cluster would appoint a leader for that particular topic. For example, initially, node 0 will be leader. Why is it the case? Why can't you just replicate the entries via raft like HCD does? Well, because we care about throughput. If we were to do consensus for each entry or each batch, we will just kill our throughput. And this system is all about throughput, so we can't do that. So we appoint a certain node a leader, and we give it the leads. For example, for a particular topic, you can say that node 0 would handle the initial 10 gigabytes of entries. After that, some consensus would happen, and by a round robin, some other node would be appointed a leader. So 10 gigabytes here, initial, other 10 gigabytes here, and other 10 gigabytes here. And this is kind of a round robin. So the point is that we want to spread the load so that no one node gets overloaded. We have leads-based fencing, like I talked about. Atomic rollovers. Yeah, here's a small GIF about how the CLI works. We can register a topic like this. Then we can ingest some entries like this. And to consume them, we can just consume them like this. Very simple client protocol like where is this? Oh, wow, demo time. Yeah, so I'm inside this Walrus directory.
Increase the font size a bit.
We are inside the directory. Start the cluster. This just makes a very it started. So this just starts. So this starts a 3-node cluster. Now the cluster is up. We have 3 nodes. And now we'll boot up our client. This is Walrus CLI. So like I showed in the GIF, you can just register a topic like this. And perfect. Something wrong with the past. Just restart. It always blows up when someone's watching. Try again. Let's see if this works. Sorry. Looks like luck isn't on our side today. Well, essentially, what's supposed to happen, I can just show you what's supposed to happen. This is what's supposed to happen. I'm supposed to register something, it's supposed to work. Then I was supposed to adjust something. I'm supposed to take it. It's fine. Sure. This was Walrus. Any questions? Yep.
I noticed something about the schema.
Mm-hmm.
Do you have some schema in each topic, or is it a separate schema? In Kafka has a separate schema service.
Yeah, so this is how it's stored in a block. Each block is just a list of entries, and each entry has some metadata. Essentially, it has your checksums, which topic it is owned by, and then your data. So in case of a bit fraud or anything goes wrong on your disk, you know that your data is gone and you need to read from another replica. I hope that was the question.
No.
Okay.
I think he's talking about Kafka. So in Kafka you have a schema registry that encapsulates the message
okay.
like Ansible. I think that's what you meant.
Yeah.
Yeah.
Oh yeah, so Walrus doesn't have any schema. Your data is just a blob which you serialize yourself. Walrus doesn't serialize anything. You need to serialize it and just give Walrus a bunch of bytes and just ingest them and fetches them for you.
So you can still use Ansible.
Yeah, you need to handle the serialization and deserialization yourself.
30. You can use 30.